Quadratic forms and automorphic forms.
All right, so just a couple more announcements before the second talk. So first of all, there are a couple of people I want to introduce. David Rowe, who's there in the back, and Sylvia Aducci, who is here. They will be ombudspersons during the evening session. So if there are any issues that come up, complaints, and there aren't organizers around, or you'd rather talk to a fellow student than to an organizer, please go to either one of them, and they'll relay your concerns to us. And then also Annette has another announcement.
Just one quick thing. When you guys go back to the hotel tonight, your sessions for working throughout the night till tomorrow morning and the next morning and the next morning are going to be tonight in the main hotel lobby in Wildcat 1 and 2. So right there offside the lobby where we had registration and stuff the last past year or two. After that, you'll be back over in the big salons where we had registration and reception last night. So you'll have salon B and C over there for you over there. So just tonight's different. So just make sure you're in the main lobby tonight. Okay?
Okay, so it's my pleasure to introduce John Hanke to talk about quadratic forms and automorphic forms.
Great. Thank you. Can everyone hear me? Okay. So it's ironic we took so much time to get the color just right because my handwriting is so bad that I don't think it's going to really matter. But if people have trouble reading anything, please feel free to let me know. Okay. So my series of talks here is supposed to be talking about quadratic forms and their connection to automorphic forms. And they connect in lots of different ways. And actually, to really set this up properly takes a long time. And so in 4 lectures, I'm going to do the best that I can. Each lecture is going to have its own theme. Today, I'm going to talk about just basic facts about quadratic forms over the integers and over the rational numbers, over a field and over our favorite ring, and things to do with local fields relating to this and a local global principle. A lot of the things that I'm going to say will overlap with other people who are speaking. So for instance, some of the theory over fields or over the rational numbers overlaps with Professor Parmalo's talk that we just heard. Things about local global things will overlap with Professor Conway's talk about the genus of a quadratic form. And things to do with theta functions will overlap with Professor Elke's talk. So I'm going to try to take advantage of that overlap. If there are things that I say that don't make sense, please feel free to come talk to me afterwards and we'll try to make the difference. Okay? So I have to define what I'm talking about. So quadratic form, I started writing a little bit early. Of a quadratic form, I'm going to mean a homogeneous polynomial of degree 2 with coefficients in some ring, R. We will often take R to be, so R is some ring, but I'm really going to think of it as the ring of integers of a number field. Okay, that's going to be my favorite example. Or you could take it to be a field. And the field, I'm always going to have the characteristic not equal to 2. And the reason for this was described in Professor Parmalo's talk. It's much more difficult to deal with quadratic forms as symmetric bilinear forms if the characteristic is 2. They're really different kinds of objects. Okay? And so when I think about a quadratic form, I really mean this. If the characteristic is not 2, I can also think of it as a symmetric bilinear form. So that's another definition that one can give. You can associate to Q a symmetric matrix. So you can write Q of x as equal to a matrix product, x transpose times A times x. Maybe I shouldn't put dots there. Okay. Where this is A is some symmetric n by n matrix over the ring. Okay. Now you have to be a little bit careful how you do this. You can't always do this over the ring. So oftentimes, if you want to do this over the ring, then you can take it to be 1/2 of this. Because the symmetric matrix, if you write a quadratic form as a symmetric matrix, you have to take half of the off-diagonal terms. So for instance, if you have x squared plus xy plus y squared, then this corresponds to the symmetric matrix. This is x transpose, let's write it like this, xy times the matrix 1, 1/2, 1/2, 1, times xy. Okay? And so if you want this matrix to be defined in your ring, you really have to take double of it. Okay? And then to recover the quadratic form, you get half of it. Oftentimes it's customary, so if I want to put a half here, then I can make this a 2, a 1, a 1, and a 2, or you can put the halves in the matrix. Okay? If you put the halves in the matrix, so if you take A to be in 1/2 of the symmetric matrices over R, then this is the gram matrix of the quadratic form. Or you can take A to be in the symmetric matrices over R, in which case this is the Hessian matrix. So the matrix of mixed partials, partial xi, partial xj, of the original quadratic form. Okay, so this is the one that's sort of a little bit better for arithmetic, but this is the one that's a little bit better if you like to think about your quadratic form as a bilinear form, because it's actually inherited from this bilinear form. Okay? If your field is if you're over a field of characteristic not 2, it doesn't really matter which way you do it, and so it's often common to do the gram matrix. And so I'll be doing that as much as I can. So since I'm going to be over the integers, I'll always be able to divide by 2 and allow myself a rational matrix. Okay? So just be aware that this is a slightly more natural notion, but a little bit less standard. Okay, so that's another way to think about quadratic forms. So there's as a polynomial, as a matrix. You can also think of it as a quadratic lattice. Embedded inside of a vector space equipped with a quadratic form. Okay? So if you think about the ring as being the integers, you can think about your quadratic form over Q. So just by allowing your elements xi, xj to be in Q, and then you can think about the z values as sort of discretely sitting inside of that vector space. Okay? And so when you do that, you have some vector space. So let's say I have x squared plus y squared, and I think about it over the integers, then it'll sit as a square lattice inside of the vector space of quadratic form x squared, so this is over z, sits inside of x squared plus y squared over q, and this is what I'll call a quadratic space. Can you still read this? Yeah. Quadratic space. Okay. So those are sort of the three ways of thinking about the quadratic form, either as a polynomial, as a matrix, or as a lattice. Okay? And I'm going to freely move between them. It's not that it's so hard to move between them, but it's kind of, to write it all down is a little bit of a pain. So I'm going to, for every given time I want to talk about it, choose one way of talking about it, but they're all equivalent. Okay? Great. So that's what I mean by a quadratic form. There's also a notion of equivalence of quadratic forms. And whenever you define something up to equivalence, you have to sort of decide what you care about, and your equivalence should preserve that. Okay, so our main question. Okay. So our main question that I'm going to be interested in throughout all of these lectures is what values in R are represented by the given quadratic form Q of x. So you're going to fix some quadratic form, and you're going to look at i.e. Q of r to the n is equal to what? So quadratic form n variables, and that's the question I want to answer, or try to understand throughout these lectures and their connection with automorphic forms. Okay. So for this, we have several notions of equivalence. Depending on how you think of a form, if it's as a polynomial, so q of x is equal to the sum Cij, xi, xj. This is up to a linear, invertible change of variable. So it's linear, which will preserve the quadratic nature. It's invertible, so it likes to be a symmetric relation. Change of variable. Like that as a matrix multiplication if I want to. If you think about it as a matrix, so if you take Q and you associate it with some gram matrix A, then A1 is equivalent to A2. If and only if there's some matrix Q, there's some U in the GL and the K R. So that U transpose times AU is equal to A1U And the reason you get it is because you have two quadratic forms that are equivalent. So if you had Q1, these are associated to two quadratic forms.
I can hear microphone stuff.
Yeah.
I mean, I can hear mine, but.
Hello? No. Uh-oh. We're experiencing technical difficulties.
I think it's not running. Still hearing in the background.
Yeah, but
Better now?
camera one.
Is it better now?
Yeah.
Okay, the battery is low. That's what happens to the yellow light here. So whoever has batteries. Okay. Awesome. Can you hear me now? Hello? Okay, great. Okay. So the reason that we have this equivalence is just because if you think of this as associated two quadratic forms, Q1 and Q2, then Q1 is equal to X transpose A1X, and if you substitute in X is equal to UX, then that will transform the matrices in this way. Okay? So that's the idea. So these are all the same notion of equivalence, and the third notion of equivalence that's really important is the equivalence of lattices. Up to isometry. And this is really looks a little bit different the way that we think about this. So here, what you're doing is if you think about your quadratic form as a lattice, you're changing basis on your lattice. Okay, and so you're never moving your lattice in your fixed vector space. Okay, for these two notions. But here, I may have different lattices that sit in the same vector space, but they're isometric. So I could take one to the other, mapping the values of the quadratic form to the values of the quadratic form on the other, and that's what I mean here. So this is up to an isometry, meaning up to an element, i.e. multiplication, by some alpha in the orthogonal group of the quadratic form, or of the quadratic space. So V is equal to the quadratic space. Okay. So that's what I mean by equivalence of quadratic forms. Okay. So now that we've set some basic notation, I just want to talk about the structure of what we know about quadratic forms. So we've already heard a bunch of things in Professor Paramala's talk, which I'm going to try to take advantage of. So you can associate some invariants of a quadratic form. So in particular, the easiest invariants you can associate are its dimension of Q, which is the number of variables. Okay. And you can write the quadratic form as a matrix A in various ways. Okay, I'll take the Hessian matrix in this case, but it really doesn't matter which way you do it. I can also define the determinant of the quadratic form, okay, which is the determinant of the associated matrix A. Okay. Now the determinant is not a well-defined quantity. It's only defined up to our change of variables, and our change of variables is by something in GLN of R. Okay? And this multiplies on one side by it and by its transpose, so the term is only well defined up to a square in R. Okay? So this is really not as a number, this is in R, so it doesn't need to be a unit, but if it's over a field, we'd like it to be a unit usually, up to a square in R. Okay? And this is here, the determinant, this is since the determinant of U has to be a unit in R cross. This is up to a unit square in R. Okay? So depending on where you are, if R is equal to Z, then this means that the determinant of Q is actually a well-defined integer, because only squares of integers, or only units in the integers are plus or minus 1, and you square it. But if I talk about the ring being the complex numbers, well, then this doesn't do me such a good job, because the determinant of Q is in the complex numbers modulo the squares of the units of the complex numbers, but every complex number that's not zero, I mean every complex number is a square of another one if it's not zero, so the only two possibilities are here is in the set 0 or 1. Okay? So depending on where you are, this is maybe a better or worse invariant, but these are two sort of simple invariants you can associate to a quadratic form. Okay. Cool. So structural theorems. So it's really useful if you want to understand a quadratic form over Z, to think of it over Q, and more generally to think of it over a field. Okay, and to see what you can say about quadratic forms over fields. So we say that Q is non-degenerate. So here we're going to take R to be equal to K, which is a field. And again, the characteristic is not equal to 2. Okay. We say that it's non-degenerate or irregular if the determinant of the quadratic form is not equal to 0. Okay. So the determinant is 0, so we're over a field now, and so every non-zero element is invertible, and so really this is the sort of the odd man out in terms of the invariance for the determinant, okay? Because everything else is up to a unit square. This is the only non-unit here. And so in this case, there's a theorem, which is not hard to prove, that says that if the determinant of Q is equal to 0, then this means that Q can be written, say it like this, it's isomorphic over K. This is the equivalence relation over K. Should have said that before. Okay. To some other quadratic form Q prime. So this is in n variables. This is in n minus 1 variables. Direct sum, so orthogonal direct sum if you want, with the form 0x squared. This is what I think Professor Parmala mentioned this result. The idea is just that if you look at the associated bilinear form, if you look at B of xy, which is the associated bilinear form, then this is equal to x transpose ay. If you know the determinant is 0, then that means that the matrix associated to this, so determinant of A is 0, means that there exists some vector x so that x transpose, so that x transpose A as a linear form is equal to the 0 vector. So this x transpose A is something like this. If this happens, then that means that the associated symmetric matrix A in this basis, so if you'd have a basis which starts with the vector x and then something else, this x not equal to the 0 vector, then that means that this has to have a row of all zeros. Okay. So star, star. But then you know that since this is a symmetric matrix, so these have to be zeros as well, and so you can just split off an entire submatrix here. So this is the submatrix of Q prime. Okay. So that's just a sketch of the proof. So in general, we'll think about a quadratic form being non-degenerate because we can continue to do this process until the quadratic form is not degenerate. Okay. So that's the first thing. Let's see. Yeah. I guess it's kind of useful to talk about how you think about equivalence. So equivalence via symmetric operations, symmetric elementary operations. So usually when we represent a quadratic form, there are lots of ways to think about it. And the best way for computing with it is to think about it as a matrix. So I'm going to think about a quadratic form. So let's say this is x squared plus 2xy plus y squared. This is associated to some symmetric matrix, okay, which we'll call A. And this is the gram matrix of it. So I'm going to put 1s on the diagonal because that corresponds to where x and y as variables are. So that's the x squared term, and that's the y squared term when you multiply out the x and the y from the two sides. And then the xy term has to be distributed evenly over here. There's a 2 here, so I put a 1 and a 1. Okay? So what you'd like to be able to do is to understand how you do equivalence on this, and you do it by taking some matrix U and multiplying here, and some matrix U transpose over here. Since you can write any matrix in GLN in terms of a product of elementary matrices, the fact from linear algebra, Right? You can try to understand the operations of equivalence on A in terms of these elementary operations. Okay? And so when you do that, the elementary row operations, the operations on this side turn into elementary row operations, and the operations on this side are elementary column operations. Okay? And so you can understand the equivalence of quadratic forms in terms of just doing elementary operations with the rows and the columns. Okay? So let me just give an example. So if this quadratic form, if I compute its determinant, then the determinant is 0. So I know this quadratic form is degenerate, and so I'd like to find a vector that represents 0 here. And so what you can do is you can try to either complete the square here or play around with entries here. And so if I do the transformation that takes x goes to x minus y, and y goes to y, then this will give me the quadratic form x minus y squared plus 2 x minus y, y plus y squared. And this is x squared minus 2xy plus y squared. It's okay? Okay. Minus 2xy plus y squared. This is 2xy. I should never do this. Minus 2y squared plus y squared. And if you add everything up, the y squareds cancel. The minus 2xy and the plus 2xy cancel. And so this is equal to x squared. Okay. Great. So you can see how hard that was, right? So we never want to do that. Okay. So a faster way of doing the same thing, much faster, is to think about the matrix A as equal to 1, 1, 1, 1, and then I'm going to perform an elementary row operation, but every time I do that I have to perform an elementary column operation as well. This will preserve the symmetry of the matrix. Okay? So what I'd like to do is I'd like to use this 1 here as a pivot to cancel out this one, and so I can take this row and add a multiple of it to that row. So I'm going to take this row and subtract from that row. Okay? So this will give you something that looks like, if I do one operation on the row, on the columns, give me 1, 1, 0, 0. Okay, so this is C1, C2 goes to C2 minus C1. Thank you. And then you do the same thing on the rows. R2 goes to R2 minus R1, but you do it afterwards, right? Because you already multiplied on the column side. So then I take this row and subtract it from this row, and this gives me 1, 0, 0, 0. And that's the same thing. And so it's really kind of useful if you want to see what's happening in terms of equivalence of quadratic forms, to see it in terms of these elementary operations. Okay? And then it's not mysterious at all what's happening. I'm using this 1 to cancel out this to get the zeros. And so this is the same thing as the quadratic form x squared. Okay? That should be much clearer. Okay? There's really no content to it, but it's a really useful way of writing things down. Okay. And I'm going to try to use it as I go through these proofs of various things. So for example, another theorem that one can prove, and Professor Paramala already proved it in sort of vector language, is that if Q is non-degenerate, or Q is regular, then if you happen to have some vector v of length 0, where v is not the 0 vector, then Q is isomorphic to, you can split off some hyperbolic plane, direct some Q prime. Okay. So the proof of this is really nice. In terms of the matrices, you can say, okay, well, I have some vector of length 0, it's not the 0 vector, and so that means that my Q is equivalent over K to some matrix with a 0 somewhere on the diagonal. I make this my first basis vector. Okay. And everything else is a star. And then you know that it's non-degenerate, so you can't have a whole row of zeros here. So it has to be some non-zero entry somewhere, let's call it A, which is not equal to 0. Otherwise it'd be degenerate. Does that make sense? Okay. So once you have this entry, then you can use this entry, you can normalize, because this is the inner product of this is the inner product of x with some other basis vector, you can stretch that basis vector so that this is 1. Okay? So stretch the basis so that a is equal to 1. Okay? So that means I have a 1 somewhere here, and I can change the order of the basis to arrange that this is equivalent to something with a 0 and a 1 here, and so it's symmetric. So it looks like this, and then there's a whole bunch of other stuff. Star, star, star. Does that make sense? So I'm just pushing around the matrices, but it's really easy to see what's going on here. Now what we need to do is we need to arrange that we can find some vector here. This second basis vector has to have length 0. Okay? If we do that, we split off a hyperbolic plane, and then we'll be done. To show that we split off the hyperbolic plane, we just need to show that we can cancel all of this stuff. And we can certainly do that, again, with elementary row operations. Okay? So to show that this is length 0, then if your first basis vector is v and your second basis vector is w, so your basis looks like this, then you can change w by w plus some multiple of v. And because this value here, because q of v is equal to 0, essentially, this will be a linear operation. So this we'll scale this by adding some multiple of an element, and so we can arrange that this matrix look like 0, 1, 1, 0. Okay, so this implies this 0 right here. Star, star, star. Okay. So if you believe that this matrix is also equivalent to x squared plus y squared, then you can just diagonalize this and you can use these pivots to cancel out all the stuff to the left and the right, and so you can make this to be 0, and so this is also 0 as well. Okay. So that's just sort of an application of this perspective from the matrix point of view. Okay, so it's kind of easy to see, aside from my handwriting. Okay, any questions? Okay, I'm already flying a little bit behind, so let me just mention some quick things. So Professor Parmala talked about isotropic and anisotropic vectors. Okay, so we know that Q is isotropic if there exists some vector v not equal to 0, such that Q of v is equal to 0, okay? And anisotropic otherwise. Okay. And we care a lot about quadratic forms over local fields and over the rational numbers, and so I should talk a little bit about those right now. Let me just see. Okay. So a local field is some field k, by which I mean either the real numbers, the complex numbers, the p-adic numbers. Okay, these are Laurent series in P. If you haven't seen them before, that's a concrete way of thinking about them. Or finite extensions of these, but I don't want to get involved in that, so I'm just going to say the p-adic numbers, and everything should work for extensions of them. The field Q2 is particularly annoying for the theory of quadratic forms, and I'll make comments as to when that's really important, but I just want to think about things over Q and Z for now. Okay. So over local fields, you can ask when is a form Q of x anisotropic. You can ask how do you classify Q of x up to equivalence. And these are really useful things as well. And you can also ask when does Q of x represent all numbers, meaning all elements of the field. Okay. So this is called a universal. To characterize things up to equivalence, we'd like to understand invariance. So a complete set of invariants for the quadratic form. Okay, we have two of them already. We have the the number of variables and the determinant. Okay. And we like to understand when a quadratic form is anisotropic or isotropic. Okay. So just some quick questions we'd like to answer. So let me try to answer them. So I guess I'll just put down some theorems. The hyperbolic plane, okay, is always universal over any field. Okay, so if you care about representing numbers in your quadratic form as a hyperbolic plane in it, it represents everything. And the proof of this is just, h looks like 2xy, so if you fix an x that's not 0, you can always scale by y. So that's easy. To characterize when the quadratic form is anisotropic, we already saw in Professor Palomalu's talk that if k is equal to the real numbers, okay, then we need to represent positive and negative numbers. So we know here that q is isomorphic to some number of 1s, so it's a diagonal form, together with some number of minus 1s, so p plus and p minus. So you can have a form in any number of variables that represents that is anisotropic. So too fast? Okay. I'm just a little bit nervous about time. What time do I have to finish because of the technical difficulties? Great. Okay, so let me go a little bit more slowly. So let me just look at what things look like over local fields. Okay, so quadratic forms over local fields. Okay. So let's say I take the field to be the complex numbers. So maybe I just put down a theorem that I didn't prove, but this is important. Any quadratic form can be diagonalized over a field. Okay. Oh, in characteristic not 2. And the proof of this is just that if you have some quadratic form over the field, then it's either diagonal or there's some non-zero off-diagonal entry. Okay, so the proof is either you have some entry on the diagonal that's not 0, or it is 0. Okay. If you have a non-zero entry on the diagonal, you can use this as a pivot to cancel out all the things in that row and column, okay, just by symmetric operations. Okay. If this is equal to 0, if a is equal to 0 here, so I'll call that a, then we'd like to somehow arrange to make it non-zero and do the same thing. And you can do this by taking there must be some non-zero entry, so that I have something like a 0, but then there's some entry here which is non-zero in its row. And so you can use this and you can add this to that, and similarly add up with symmetric operation to mean that this entry here is non-zero. Okay, so this is the idea. And then, so this is now not equal to 0, and you can use this as a pivot to cancel out all of the entries. So once you do that, this means that your matrix looks like some A with zeros, and then some star, and you can repeat. So that's the proof. Okay. And that's extremely useful because now I'm going to go through the local fields and characterize the quadratic forms. So if k is equal to c, okay, then we know we can always diagonalize it. We know we have a1 through an on the diagonal. And we know that these entries can be adjusted up to some square entry in the units, because I can always rescale. And so since every non-zero complex number is a square, we know we can always make them all equal to 1. So every quadratic form looks like the sum of squares form over C. So it's pretty easy to characterize forms over C. Over the real numbers, the quadratic forms, again, look diagonal. But now the entries of the square classes in the real numbers, so let me just say that r cross mod r cross squared is represented by 1 and minus 1. So that means that I can adjust each of these a sub i's to be either 1 or minus 1, but I can't switch between them. Okay. And so this means that q is equivalent to some number of 1s on the diagonal and some number of minus 1s on the diagonal. So that's how you can characterize quadratic forms over R. You can characterize in terms of the dimension and the number of 1s and the number of minus 1s, which add up to the number of the dimension. Okay. Sometimes people use this invariant called the signature to do that, which is this p plus minus p minus. So if K is equal to a p-adic field, things become more interesting because the square classes are more interesting. So here we still know that Q is a diagonal form, A1 through AN. Okay? And we know that the A sub i's can be chosen to be representatives within the square class. So this is in Q cross, mod Q, QP cross, mod QP cross squared. Oh, it's down a little bit. So what are the square classes here? So if P is not equal to 2, okay, the square classes are represented by a 1, so the unit square class, the square class of a non-square unit, so this is U, where U is not congruent to a square, mod P. And then there's P, and then there's PU. So you saw these appear in Professor Paramala's talk because she constructed an anisotropic form in 4 variables over QP. She did it from a quaternion algebra, and this was these were the square classes that were represented on the diagonal. Okay. So this is a theorem that this is what the square classes look like. When P is equal to 2, we have 8 possibilities. And if you have some extension of Q2 that's ramified, then you certainly have more. Okay. So how do you characterize quadratic forms over QP? Well, you can always adjust them to be diagonal forms with one of these things on the diagonal. And so you have invariants, which are given by n and the determinant. And so you can ask if this is a complete set, if this is a complete set of invariants for your quadratic forms over QP. So if I have 2 quadratic forms with the same determinant and the same number of variables, are they isomorphic? And the answer is no. So this is not complete. So we need some more to distinguish. And as an example, I'll leave it to you to check. If I look at x squared plus y squared in Q3, then this is not equivalent over Q3 to 3x squared plus 3y squared. But they have the same invariance. They have the same invariance in terms of the number of variables. They're both 2 variables. And the determinant in this case is 1 times 1. In this case is 3 times 3. But 9 is in the same square class as 1, and so they're the same. So there's a theorem that allows you to complete this. And the answer is basically, this is almost a complete set of invariants. You need one additional thing. You need a number which is either plus or minus 1. Okay? And depending on how you write down this invariant, you might call it the Hanke invariant or the Clifford invariant. But basically, it's a plus or minus 1, and you get it somehow from the quadratic form. Okay? And it should distinguish between these 2 things, and this one will have invariant plus 1. This one will have invariant minus 1. Okay? So the theorem. So let me write down what this is. So a complete set of invariants of quadratic forms over QP. And I mean of non-degenerate. I always mean non-degenerate now. Quadratic forms over QP is given by the number of variables, the determinant, and this thing called the Hanke invariant, okay, which I'll define for you now. So if you look in the literature, there are different ways that different authors define this invariant. So whatever you're using, just be sure when you look at it that you know which invariant you're talking about. Okay. Yes?
And this works over P equals 2 as well.
This works over P equals 2 as well. Okay. So I'm not going to prove this theorem, but I will at least try to define what the CP is. So the definition of CP. So what you do is you can take the quadratic form and you can always diagonalize it. So this A1 through AN. Okay. And then there's something called a Hilbert symbol, which is a very deep thing, and I will not have time to talk about it all. But the Hilbert symbol, it takes 2 square classes, and it gives you back a plus or minus 1. Okay. So the Hilbert symbol of A and B, so this is a really defined A and B are in QP cross mod QP cross squared at P, is defined to be either 1 if the quadratic form ax squared plus by squared minus z squared is isotropic over qp, or minus 1 if not, if it's anisotropic. So that's the definition of the Hilbert symbol, AB on P. And it's something that you can readily check. It has a lot of really great properties. It's multiplicative, which is not clear at all from this definition. It takes some work. And it's very closely related to class field theory. Okay, so this really is an object that comes from class field theory, but we can write it down in this case in terms of quadratic forms. Okay. So having said that, let me, I can't do that. I'll try again. So the definition of the Hanke invariant is I take the quadratic form and you over QP, you can diagonalize it through A1 through AN. And then CP is defined to be the product over all of the diagonal entries. I take them pairwise. Okay. So I'll take I less than J, and I'll take the product of all of the Hilbert symbols, AI with AJ. Okay. This is a product of plus or minus ones. It's not clear this is well defined. Okay, I don't have time to say that either, but it is a well-defined thing, and that is the additional invariant you need to distinguish between quadratic spaces over QP. So that concludes my discussion of local fields. What I really wanted to talk about are rings of integers. I haven't talked about the integers very much at all, so now I'd better do that. Okay, so let's see, 10 minutes. Okay, I'll state a quick theorem. So let me just show you how to work with quadratic forms over ZP. I won't have time to really explain what's going on here, but there is a theorem which lets you almost diagonalize a quadratic form over ZP. Okay? Now over ZP, it's different from working over QP because I can't divide freely anymore. If I divide, I might change my valuation, I might leave ZP. Okay? But if I have quadratic form that is always equivalent, so this is non-degenerate. Well, I guess it doesn't need to be non-degenerate, but is equivalent over ZP, meaning the changing variables I have are now in the p-adic integers. P-adic integers are a Taylor series in P, if you think about it in terms of the p-adic numbers of the Laurent series in P. Then Q is always equivalent to some quadratic form, some diagonal quadratic form, A1 through AN. If P is not equal to 2. And the reason for this is that we can sort of look for the element of minimal valuation, okay? And we make that our first basis vector. Okay? We arrange in the same way that we want to have a pivot that we can use to cancel everything else. If you have something of lowest valuation, you can move that to the upper left entry. You can use that to cancel everything else because everything can be a multiple of it. Okay? And so that's the idea. Okay? And it's equivalent over Z2 to some sort of block diagonal form. So maybe I should write it like this. Okay. This is block diagonal with block size less than or equal to 2. Okay. So it could be diagonal, but you could also see some 2 by 2 blocks appearing. And the reason is just because if you have an entry which has the lowest valuation of 2 off the diagonal, you can't get it onto the diagonal because your symmetric operation is going to add 1 multiple this way, 1 multiple this way, add 2 multiples, but then I've changed its valuation. Okay. So that's the idea. That's all I'm going to say about that. Okay, so that allows you to work with quadratic forms over ZP and over Z2. There's a way of making this a little bit more precise and keeping the p powers being increasing when you go along this diagonalization process. And this diagonalization process is not a complete invariant. If p is not equal to 2. Okay. I'm not really going to explain this except to say that when p is 2, there's a way of writing this down in such a way that you can make a complete local invariant over ZP from it. When p is 2, you can't. Okay, you have to do something additional. Okay. So I haven't given you a way of talking about quadratic forms over ZP completely yet, but I want to talk about Z. And so first I want to talk about how you assemble local to global information. this is called the Hanke principle. And what it says is that if I have two quadratic forms, which are equivalent over the rational numbers, well, certainly you know that they must be equivalent over the p-adic numbers for all primes p and over the real numbers. Because the rational numbers sit inside of those fields, and so the change of variables over q is a change of variables over all of those other fields. Okay? So this means that q1 is equivalent over all places v to q2 for all places v. So v runs over all the prime numbers and something that indexes the real numbers as well. It's called a place. The Hanke principle says if I happen to have two quadratic forms over q, and I check that they're locally equivalent at all of these places, then they're also equivalent over q. Okay? This is called a local global principle. This is the hard part right here. I'm not going to prove that part. Okay. It's called a local global principle because it's easy to understand local information and we have complete invariance to check if two things are isomorphic there, but it's harder to understand global information. So this is what really gets you going in terms of this philosophy. Okay. Now, you can ask, what about a local global principle? So this is also true over any number field, by the way. Is there a local global principle over z? If I have two quadratic forms over z, and I know they're locally equivalent over the p-adic integers for all primes p, and over the real numbers, are they equivalent over z? Okay. And the answer is no. And I'll put down an example. I'll let you verify for yourself. This example is true. X squared plus 11y squared is not equivalent over z to x squared plus 55y squared. Okay? But they are locally equivalent everywhere. Okay. And to see this, I'll just make a quick comment. You just need to check they're locally equivalent at all primes not dividing the determinant. So all primes that are not 5 or 11. Well, if it's not, you need to check it's equivalent at all primes dividing the determinant. The other ones come for free, okay, once you check the other invariants. Okay, so these have the same determinant and number of variables. And so you're using really the fact here that 5 is congruent to a square mod 11, and 11 is congruent to a square mod 5. Also mod 2. So let's just say, to be fair, p equals 2 and over the real numbers. Okay, so they're both positive, definite, and 2. Okay, so what can one say about this? Well, this is bad, right? Because you want to use local information to assemble information about the integers, but there's a theorem that says that there are only finitely many equivalent quadratic forms, equivalence classes of quadratic forms over z, so meaning that I have equivalence over z, okay, which are locally equivalent. At all zv. So this means that if I look locally at a quadratic form, I may not be able to distinguish between at most finitely many classes of forms over z. Okay? And so that's not so bad, although a finite number can be a large number. That's certainly true. So we define the genus of the quadratic form to be equal to the set of all quadratic forms over z. This is quadratic form over z, which are equivalent to our given quadratic form over zv for all places v. Okay. That means they're locally equivalent over the integers everywhere, and over the real numbers, I take the integers to just be the real numbers. And so this theorem, which is due to Siegel, it's the same thing I just said, says that there are only finitely many classes of quadratic forms in the genus of Q. Okay. And the proof of this theorem, which I definitely won't be able to give, uses reduction theory. But I can give an example of what this means. So reduction theory means I'd like to be able to take a quadratic form and change its coefficients so that they're as small as possible and still giving the same quadratic form. Okay? In terms of a basis, this means I'd like to have a basis of my lattice that is as orthogonal as possible of shortest possible vectors. Okay? There are several ways to say this. If I have a quadratic form in two variables, which is positive definite and non-degenerate, then we know that Q of x, y, which is ax squared plus bxy plus cy squared, is always equivalent to some quadratic form, to some q prime of xy, such that absolute value of b is less than or equal to a is less than or equal to c. And there's actually some further conditions, just like what happens when they're equal. But you can always change variables so that this is true. And once you have this, then you see that for a fixed determinant, also, if the determinant of Q is equal to delta, okay, maybe delta. Usually people call the discriminant, so let me just say the discriminant. So this is b squared minus 4ac. Then it's not hard to see that a times c is less than or equal to the absolute value of delta over 3. So the discriminant agrees with the determinant. I think it's maybe 4 minus 4 times the determinant of Q in the way that I've written it. And so from this, you can see that if I have any quadratic form that's equivalent to my given one, it's going to have the same determinant. Okay? And so I can arrange for the, so I know that the coefficients a and c are bounded by this number. Once a and c are bounded, then b is bounded as well. There are finitely many choices. Okay? And that's how you prove this theorem. So I really have to finish up now. So let me see what else I wanted to say. Oh, right. So I won't be able to say this, but let me just make a quick comment. Okay. So, so what you'd like to be able to do is to study the genus of Q. Okay. And in particular, you'd like to construct all classes in the genus of Q. Okay. So for binary quadratic forms, you can do this just by the inequalities we've written down already. Okay. But in general, it's kind of hard. Okay. And so there's this method called the neighbor method, which I'm just going to say how you do it, but I'm not going to really prove anything about it. And this is written most conveniently in terms of lattices. Okay, so I'm just going to write them in terms of lattices. So given quadratic form Q, I'm going to think of it as a lattice L sitting inside of some quadratic vector space. Okay, this is a lattice. And what I'd like to be able to do is to construct another lattice in this vector space, which is isometric to this one locally everywhere. Okay? That's the idea. And so the neighbor method is going to produce this. So you start with L, okay? And you're going to form a sublattice, so you fix a prime P. And P, I'm going to take not equal to 2, and maybe just to make myself feel better, I'll say P doesn't divide the determinant. Not that it really matters. You can also do neighbors when P divides the determinant, but it's a little bit more complicated. And so I'll form a sublattice in this of index P, with given a vector. So this is, I'll call L sub V 0, which is going to be the set of vectors x in the lattice. Okay, so the lattice is now, you have some basis if you want, such that the associated Hessian bilinear form with V as a multiple of P. Okay. Now, for this to make sense, I'd like to have the vector V to be in the lattice, and I'd like to have Q of V to be some multiple of P. Okay. So this is a sublattice of index P. So long as P is not in, so long as V is not in P times the dual lattice of this intersect L. Okay. So whatever that means, there are lots of ways to think about this bilinear form. One way to think about it is giving a dual lattice inside of the quadratic space. Okay. So this condition means that the vector v is actually in this sublattice, LV0. I guess I need to say one other thing, that Q is primitive. So what this means, this bilinear form is integer valued. And so in particular, this means that L is contained in its dual lattice. And so this is going to be some sublattice of index P. You can see that because the map from this to, from L to Z, given by this bilinear form, surjects onto the integers. And its kernel is something of index P. Okay, so that's the idea why this is a P here. Okay. Then from this, you can adjust V so that by some element of the sublattice, so that V actually has values in P squared. Okay. Okay, this is by some element of the sublattice. So I'm just using V to construct the sublattice. So this construction is independent of if I adjust it, if I shear it by some element of the sublattice. And then I'm going to define a superlattice of this, of index P, to be LV0 plus 1 over P times the vector V. So what is this now? This is this lattice that I started with down here, but now I'm going to add to it 1/p of the vector V. Now, the vector v has values in p squared, z, and so 1 over pz, 1 over pv, sorry, 1 over pv is going to have values in z. Okay, so this vector v that I put in is now integer valued, and this this lattice has index p in this because I'm taking 1 over p of v, so there are p copies, p cosets. Okay? And so the claim, and this is where I'll stop, which is a theorem, right? It's the theorem. Should be clear, okay. Is that this other lattice, neighboring lattices to L lie in the genus of L. Okay. So this going down and going up construction is going to produce another lattice, and there's an isometry that you can use to show you a local isometry, a local symmetry, in fact, the type Paramala talked about, to show you that this neighboring lattice actually constructs things in the genus, and it's a question, does this give the whole genus? In the genus, and the answer is sometimes. Sometimes. What it really does is it gives you a spinor genus, or 2 spinor genera in the genus. Okay? And I'm not going to say exactly what that means until maybe 2 lectures from now. Okay? So you get at most 2 spinor genera in the genus of L. Okay? So just to conclude, what I've tried to explain a little bit about, although I really apologize now that I look at my own handwriting, what you must be seeing. A little bit about the theory of quadratic forms over Z and over Q, and how local fields and local rings of integers help you to understand these kinds of things. Okay? So what I'd like to be able to talk about more later is how automorphic forms come into this game to help you understand what numbers are represented by a quadratic form. But that's the main question I'm going to try to continue to answer. Thank you.